All right, let's look at another harmonic motion problem. So this one says a signal buoy between the coast of Hilton Head Island, South Carolina, and Savannah, Georgia, bobs up and down in a minor squall. From the highest point down to its lowest point, the buoy moves a distance of 4 feet. It moved from its highest point to its lowest point and back to its highest point every 14 seconds. Find the equation of the motion for the buoy, assuming that it is at equilibrium, its equilibrium point at t equals 0, and the buoy is on its way down at that time. So you might need to read that a couple times, but basically this is another harmonic motion type of problem where the problem is describing how something is moving and it's oscillating. It's going back and forth and repeating the displacement from equilibrium. It's going up and down and up and down, kind of like a sine or cosine wave, right? So this is another harmonic motion type of problem. When we do this, just like before, we always want to graph it. Let's try to put this on a graph, and then we want to try to, from the graph, make an equation. Okay? So let's start off by trying to make a picture here. We have a graph, and it says from the highest point down to its lowest point, the buoy moves 4 feet. So let's assume that the equilibrium point here is going to be at 0. Let's call this, let's call this y, and let's call this t. And so we could, one way to model this would be to say, let's go up 2 and down 2, and let's assume that at y equals 0, that's like, that's like the equilibrium point of this wave. So we have 2, and we're talking about feet here. So this is like, this is in feet, and it says every 14 seconds, right? 14 seconds. That's going to indicate the period, how long it takes for the wave to complete, right? So if we look at, let's see here, find the equation of the motion of the buoy, assuming that its equilibrium point is at t equals 0 here. So that means that it's in the middle, or the y value is 0 when the time is 0. So basically that's saying right here we have that point. We are at equilibrium when the time is 0. That's what it's saying here. We're at equilibrium when the time is 0. All right? And then, just like we think about a sine or we think about cosine, we can break up this wave into different intervals. Let's see, like 1, 2, usually we break it up into 4 segments, right? And we think about the motion from there. So if we keep reading, it says the buoy is on its way down at that time. So that means that we're going down from equilibrium when we start this, stopwatch at time equals 0, it's in the middle, and then it goes to the bottom, and then it kind of follows the path, the harmonic motion, the sine graph, right? The periodic function goes back to the middle. The next segment would be at the top at 2, and then it would just repeat itself right here. Now it says, what are my labels on the graph going to be? Well, it says the period is 14 seconds, right? So that means that this right here is going to be 14, because it's going to take 14 seconds for it to get back to where it was. So what does that mean about these, these intervals? If we want to write them down, well, that means that this would have to be 7 seconds, because that's half, and then this would be, like 3.5 here, and this would be like 10.5 if you wanted to write that. But we sort of have a picture of this motion now, right? We have it on the graph. We have the amplitude. We have the period. The graph is going to go like this if we kind of sketch it. And it's going to repeat over and over and over again, right? So we do the same thing as we did before. We think about, okay, the period, right, in this case is equal to 14 seconds. But we know that if we're using sine or cosine, the period is 2 pi over b, right? So we're going to replace this and say 2 pi over b is equal to 14. That's going to allow us to give us our frequency, our b value of the graph that we're going to, or the equation that we're going to write. Let's sidestep a little bit here and decide if we're going to use sine or cosine. Well, in this case, we're going to use sine because I'm starting like in the middle of my graph. I'm starting at equilibrium, and then I'm going to go down, right? And since I'm starting to go down, I'm going to use negative sine as my equation. So as I start to piece this together, I say, all right, well, this is going to look like y equals, it's going to be some a value. I'm going to use sine, and then we're going to have a b value. And the variable that I'm using here is time. So I'm going to say bt. And we don't have any phase shift or vertical shift that we're going to keep track of here, so we're just going to leave it like that, right? So then we just figure out what is a and what is b. In this case, a is going to be -2, right? It's -2 because the amplitude is 2 and we're going down, right, from equilibrium. As the time goes, we're going down. So this is -2 sine and then b times t. Then the question is, what is the b value? Well, that's where we started over here with the period. So if we want to figure out what the b value is, we can just solve for b. So I'm going to multiply by b on both sides. If I'm doing this, algebraically, right, the b's would cancel off. I'd get 2 pi equals 14b, and then I divide by 14 to get the b value, which if I reduce is going to be pi over 7. So pi over 7 is the b value in this situation. So I say y equals -2 sine, the b value is pi over 7 times t. There's my equation for this problem. If I'm going to double check my problem on Desmos, I can go ahead and do that. I can graph -2 sine of, what was it, pi over 7x. And so there's our graph. We can make sure that these kind of critical points make sense. So time equals 0, we're at 0. At 3.5 seconds, we're at -2. At 7 seconds, we're at 0. 10.5 seconds, we're back at 2. And at 14 seconds, one complete cycle, we're back at 0 on the way down. So that verifies that this equation that we made makes sense with the problem description and that we have the right answer.